that part will remain mostly language agnostic, so you don't have to worry too much about that. Having said that, I would still prefer if everyone used Julia because it is really good. So that's all I have for the introduction. So today, if you saw the mail, I think it was mentioned, we will try to simulate a simple pendulum, the most simple workhorse of physics, right? In Newtonian physics, that's literally like the most basic model. So that's what we'll be trying to do today. I will try to share my screen. Let's see if it works. One second. Okay. I think you should be able to see my entire screen. Let me. Okay, just give me a second. Oh, nice. Yeah, so let's begin with what our pipeline will be, what our workflow is going to be. So to start with, let's go over generally what we try to do in physics, okay? Also, there's going to be a little bit of an input lag between when I speak and what actually appears on the screen, but that's not because I have a bad connection or anything. That's just how this device works. So we'll have to deal with that. Okay. So to begin with, we have some phenomena in real life, right? And we would like to somehow model it. We'd like to explain it, understand it. So we create something called a model. And you guys can see this and hear me right? I will take that as a yes.
Yeah.
Okay. Also, if you guys have any doubts or anything, please stop me right in the middle. This is not meant to be like a lecture or anything, although it might seem like that at some points. Please, it's meant to be more of open conversations, okay? So I'm prone to making mistakes too. If you spot it.
Arnav was asking, does Julia have other IDEs other than Pluto? Which
you can generally with Julia, people use VS Code mostly, or Pluto, of course. What looks like CMD? Okay, so I mean, if you just launch Julia as it is, okay, are you launching it like this? If you launch it like this is something called the REPL. Okay, it is called REPL. That is stands for read, eval, print, loop. So essentially, what you do is you give a command, it reads it, it evaluates it, it prints the result, and then it loops through it. Again, waits for your next command. So Python also has this. Most interpreted languages have this kind of thing. So if I just write x equals 1 or something, it evaluates and gives me 1. People don't develop on this, usually for prototyping.
So it's like the interactive mode in Python, right?
Yeah, basically. It's in general called a REPL, so that's the term I'm used to. But yeah, essentially. You give an input, it gives you back an output, so on. So you can also load scripts. You can write, open a notepad or something, write a Julia script, save it, and then load it onto this. But people do use this workflow. I don't prefer it much, but we'll be working with Pluto notebooks. So okay, right. If you guys rudely interrupted in the middle of when I was in something else, but sure, okay, let's continue in this string. If you guys install Julia, we just need 2 packages, okay? Once you're here, press the, what is this? The square bracket key, like the right square bracket. I can't type it, the key which corresponds to this one, but without pressing shift. So if you do that, you'll get into the package manager. So here, all you have to do is add Pluto, which is one package which we'll be using, Pluto UI and plots. So the first 2 are for interactivity, and basically Pluto is like the Julia equivalent of Jupyter. So it's essentially a notebook only, but it's much better as you see. And plots is just for basic plots. So just run this command, it will install the packages. While it will take a while if you're doing it for the first time. But once you're here, just press the right square bracket. So you'll go into the package manager. I will get back to this later. Yes. Any other questions regarding Julia? Okay. So, right, where were we? So we have a phenomena which we'd like to model. And in doing so, we first simplify the model. I mean, simplify the phenomena. So we extract only some parts of the phenomena into our model. And in doing so, we also abstract out some features. These terms I'll explain more in detail once we take the specific example of a simple pendulum. So once we have a model, we have physics on the side with all of its theories. So in our case, we will in these sessions we'll mostly be dealing with Newtonian mechanics only. Okay. So in general, the theories which we'll be utilizing is Newton's law, which governs dynamics of objects. So our main concern will be dynamics, but it doesn't have to be restricted. Dynamics means evolution with time, evolution of any quantity with time. Okay. So it doesn't have to be dynamics, but I will consider only in that context for now. But in general, it can. There are a lot of different results you would like to get from the model, but we will focus on time evolution. Okay. So now we've got a model and theory. Generally, once we have a theory, we use like analytical expressions, math. Basically, we do a lot of complicated math to get analytical expressions for some quantity we want, which basically means like closed form, mathematical functions, like the position of the trajectory of particles, so on. So analytical expressions. And from that, we do whatever analysis, get what we want from the model. But in some cases, this step is not possible. Simply the math is too complicated. So that's when we turn to the computer. We start looking into computational physics, which is basically a different way of, trying to explore what our theory is trying to tell us. Because some cases, once you go to really complicated situations, which is what a real world is comprised of, we never have like a single particle. There are no point particles, right? Everything's a rigid body. So there's a lot of complexity. But our theories, if you try to extend it to many particles, for instance, it starts getting really complicated really fast. And this approach of like getting an analytical expression goes right down the bill. So in those cases, we go down another route. Namely, we take the model and the theory, and then there is this black box here. I don't know what is that inside. What happens here is something I'd like to call the translation process. Basically, I am reformulating what my model and my theory are trying to say in a different form such that a computer is able to make sense of it. This step itself is only necessary because the way we structure mathematical models, with variables, functions, all of those, a computer works fundamentally different from that. Computers only, like store things in bits. Basically, the computers work with numbers. So that creates a problem because computers have finite memory, right? The whole idea of an infinite precision number goes down the bin. There is nothing exactly like 1.000. When we say 1 in physics or like generally in math, we mean this infinite decimal, right? But then most numbers, when you represent them in a computer, it only has limited memory. So after some point, it loses all the data. So the numbers which we have in mathematics and physics are not the same as the numbers we have in computers. They are just like some kind of approximations. So that poses a problem. So how do we, like map variables which are essentially continuous quantities, right? They're like, they can attain any value in some given domain. But that idea entirely goes away when we try to put it into a computer. So there is some translation process in which we try to mitigate this somehow. We have to, obviously some data we are losing, right? Because we can't have infinite precision. Some data we are losing, but we are also gaining something in the sense that the theory was literally unable to predict something for a given situation. So via the computer, we are able to get some level of, okay, some sound keeps coming. How many people are joining? Fine, okay. So by means of the computer, we'll get some result. Okay, so what that means exactly, we'll see. So once you do this, once you have translated such that the computer knows, or at some level understands what we are saying, you evolve the system or you compute some result. So that gives some kind of a result. And finally, this result is still, in the language of the computer, right? And we would like to interpret that. So lastly, there is like the inverse translation, which is translating it back to what we want. So generally, in what we'll be dealing with, this is going to be visualization, just like plotting, you could say. But in general, this doesn't have to be. This is not the pipeline of a general computational physics thing, because in research, because in that mostly the end goal is not visualization, but rather computation of some quantity. For example, if you take like a molecule, a very complicated molecule, and you want to know some kind of ionization energy or something like that, starting from like quantum theory, Schrodinger's equation and all, you can make some kind of computational program which computes this energy required to excite an atom or something like that. So based on this, like final result, what do I want from this? Based on that, this simplification or this abstraction part plays a very important role, because in physics, it's all about abstracting out the parts of the phenomena which you want to study. Right? We very rarely start from first principles. That is, we don't start like, if you want to describe a ball, the trajectory of a ball like a parabolic trajectory, we don't start from quantum mechanics and see how the individual atoms of the ball flies, right? We abstract out such that there's some kind of macroscopic entity and proceed from that. So, this first step is mostly a physics thing. It doesn't have to be a computational physics thing, but mostly what computational physics deals with is these last three boxes, the method of translation. Because the biggest problem is when we are translating, there is simply not a translation scheme which will capture the model entirely. That's just not possible, simply because of the memory issues, and there is not a one-to-one mapping between what the model describes and what the computer is capable of describing. So in that case, computational physics and a related field, which is numerical analysis and math, try to like maximize this this translation, try to keep the errors due to this process a minimum, so that what result we get at the end is mostly representative of what the model actually predicts. Okay, so let's see this quickly in the context of the simple pendulum. So initially, the phenomenon I want to describe is essentially a pendulum, right? But a pendulum is pretty complicated. This is basically a string here. The string has a mass, and it can go slack also. And this ball also has a mass which is tethered to this string, and the string is suspended from some point. So there is a lot of complexity here, in the sense that if I release the bob from a specific position, since this is slack at this position, it may undergo very complicated trajectories. We haven't dealt with that. So our first step, the simplification for our model, starts with what we consider in the simple pendulum. So can anyone tell me, like what are the simplifications we do to get the simple pendulum model? I don't want to keep speaking. So,
we assume the string to be massless, for instance.
Air resistance to be 0.
Yes.
String to be completely solid, like unstretchable.
Yes, so rigid. Essentially, we transform the string into a rigid rod, which, if you think about, is a fairly different system entirely. But sure, this is what we've done. And all the mass is concentrated in this bob. Okay, so our simplification is done. We have deemed this simple enough. In the future, I think in like 4 or 5 sessions we will be able to tackle, an actual under quotes pendulum also, where we can somehow model this slackness. But we'll have to start somewhere, and this where we shall begin. Okay, so the simplification is done. Now the abstraction. What exactly is a pendulum? What is a pendulum to you and me? It is a complicated object, right? The bob here itself is comprised of many particles. but we don't need that kind of a description. So can someone say, how can I abstract, what a pendulum is, at least for our purposes? How do I describe the evolution of a pendulum? Maybe that is a better question.
We consider it a single particle?
Sure, yes. So we consider it's a point particle. Sure. Okay, so and we see that this is somewhat in a 2D plane. The problem is a two-dimensional one. So to locate the position of the particle, we give it two coordinates, x, y, based on the standard Cartesian coordinate. So this is our setup, right? X and y. Okay. Is this the best description we can come up with? Because once I've given x and y, what does the problem become? We have Newton's law, which governs the dynamics of the problem. Like how does x and y vary? Which is basically mr double dot equals the force vector, right? So this is what Newton's law tells us. But what is the problem here? Right, this is not it. This is not it because we have a rigid rod here, rigid master's rod, right? Essentially what that does is poses a constraint on our problem. Namely, that constraint is, can someone tell me what the constraint would be? Like the mathematical form of it.
It would move in a
I will wait until someone. Huh?
It would move in a certain manner.
Yeah, so how can I describe it in terms of, the coordinates of assigned at x and y? Let's say I mark this anchor to be x naught comma y naught or something like that. So can you put the constraint due to the rigid rod in terms of a mathematical?
X square plus y square is equal to the circular equation, the length of the.
Right, exactly. So, well, since the anchor is not the origin, x minus x square, but you basically got it. So this would be equal to the length square of the pendulum's rod or the string, right? So we have to solve Newton's equation within the satisfaction of this constraint. Also, this constraint has to be satisfied, or else it will just be a ball in a 2D plane. It wouldn't be a pendulum per se. So there are ways of solving this. I guess you could use something called a Lagrange multiplier, but we will not go down that road. I've not actually tried simulating using a Lagrange multiplier. Maybe we can do that later, but that is an easier way to encapsulate this information. So can someone tell me that? That is a okay. What would you do to simplify this? This is kind of hard.
We can use gravitation in y-axis and energy equation instead.
Okay, sure, but that is not what I was looking for. Something else. We'll see. We'll think about that also. I've not thought about how that would actually be easier or not. That is a very simple. Okay, how about this? Can you make this constraint much simpler? By casting our description, we have to use x, y.
Set x naught y naught equals to 0.
It will always maintain a certain distance.
Can you just use polar coordinates?
Yes, precisely. That's what I was looking for. Thank you. So there is a coordinate transformation. Now, very naturally, it falls into r comma theta, this coordinate description. So in that case, this constraint simply becomes r equals L, right? And just like that, we've turned a constraint into a dynamical law. That basically, this is governing the evolution of one of my coordinates now. One of my coordinates, which is r, right? The radial distance. I will set my origin to be the anchor point, and the radius will be one coordinate, and the angle will be the second coordinate. So note that we still have 2 degrees of freedom. So we've not lost any information. In fact, we've simplified it because x comma y is over specifying, if you could say, the problem, because r equals L, as in this is equivalent to saying dr by dt equals 0, which means it doesn't evolve at all. So we just turned a constraint into a dynamical law, which makes it much easier to deal with, because now we only have essentially one coordinate to work with, which is the angular coordinate. So I guess we all must have done this derivation like countless number of times. We shall go through it again really quickly. So we have what? Gravity downwards. And we would like to see how this changes, right? So we get the torque, which would be minus mgl sine cosine sine theta. And this would be equal to ml square, which is the moment of inertia, times the theta double dot, which is the angular acceleration, right? So then we would get theta double dot equals g over L minus g over L times theta. Right. So this is our second dynamical law for the second coordinate. So we essentially boiled down our problem into solving this second order differential equation since R equals L. So that's done. We boiled it down to as simple. Oh shit. Okay, this is old habits. Sine theta, right? Because right here you get one limitation of analytical expressions. This differential equation as it is does not have a closed form. I think it results in something called an elliptical integral. You can't solve it per se. But we usually do that small angle approximation, right? And write it to be theta and then proceed. Then it becomes a simple harmonic oscillator. Also a huge workhorse in physics. Right. So we don't need to approximation though, because now we have the power of solving this somewhat exactly. Well, okay, we'll see. We'll see what that means. Right. Along with this differential equation, I also still need few more pieces of information. Does anybody know what we are missing? To solve this problem, to solve the evolution of this system, I'm missing some more information. Meaning, if I just gave you this differential equation,
The
can you
initial
tell me something? Yes, precisely. So, in this case, there would be how many initial conditions would you need? I mean, like what all information?
Just the angle. I mean, if you have the angle, you could just tell its initial condition.
Yeah, but think about
angle and initial velocity.
yeah.
Yes. So we've come at one point here. Can someone tell me? Can you decompose this second order differential equation into something easier to work with, which is two first order differential equations? Can anyone suggest how we could be doing that? Because this is a single second order differential equation. I'm sorry, I can't hear.
Conservation of energy.
Okay. Yes, we could do that. You guys are like really keen on conservation of energy, huh? I have not thought about that kind of an approach at all, but sure, okay. Any other way, a more direct way?
You could write d theta by dt as omega.
Yes.
Then,
Is this the same person answering all my questions?
no, this is Sahil.
He's the. I don't think he's supposed
Sorry,
to.
I can't see who's speaking. I'm not familiar enough to judge you guys by your voice. But okay, yes. So
No, but what Jishan said is also, it will lead to the same equation. What the conservation of energy will lead to the same
conservation of
equation.
energy.
So he's also
Right, okay. Cool, nice. No, this is nice. So, you guys are coming up with approaches that I did not think about, which inevitably leads to the same result, but it's still nice. Okay, so we introduce a new variable called omega, which is the angular velocity, right? These are all functions of time. And the second equation, this second order equation simply becomes governing the angular velocity instead, which in turn depends on theta. So this is like some kind of a coupled set of equations. Okay, so this is why we need two initial conditions. We need one for theta and one for omega. So hence we can solve the problem. Fine. We're finally done setting the physics stage. We have not even broached into computational aspect yet. Now we will begin. Okay. So till this part, where we have essentially come as the equivalent of this line, we have just abstracted out and set up our model. Now we need to get into how can we feed it into a computer. Okay. I don't think we'll be able to implement the whole thing today. We'll see what we can do. Okay. So where we left off? We left off at two first order differential equations. Okay, so we had this and right. So the first problem is, okay, let's write the domains of some of the variables. Theta essentially belongs to 0 to 2 pi or any analogous range like minus pi to pi also. So something like that. And omega, I guess, omega can be anything, I guess, right? 0 to, it could belong to any real number. Okay. So fine, we have specified the domains and time, of course. Time is a parameter in these Newton equations. So time, I guess we restricted to positive halves, so from 0 to infinity. Right. This is generally what we work with in physics. The problem is this entire idea of like infinite domains and all like kind of breaks down. We simply cannot store infinite data in a computer. So what we do is we come up with a compromise. We say, okay, I don't want the solution for all the time t. You know, like if you solve the simple harmonic solution, I guess you get something like sine t or something like sine omega t or something. But which is f of t. So that will be like theta of t will be equal to something of this sort. Which means I can, in principle, find the trajectory's value at any time instant. That I'm going to entirely lose in this process of making it accessible to a computer. That's gone. So instead, what I say, I will discretize my time domain. That means I will only look at the system at selected few sets of points in time. So it doesn't have to be a uniform grid, but for our considerations, we'll begin with a uniform grid, such as like some starting point plus delta t.
So basically breaking it down to frames.
Yes, I guess you could think of it like that. Yes.
Okay.
But the only point is that here I'm considering a uniform delta t, so like equally spaced intervals. It doesn't have to be that. It will become apparent if suppose here the solution is like what sine t, something like this we'd expect. So here, if I took it at uniform intervals, it somewhat represents the actual trajectory. So we are kind of good. But there are some functions which would like suddenly like oscillate, and then at some other places the behavior is much less erratic. So in that case, if I still have uniform ones, like uniform sampling of the trajectory, I'm going to get a vastly different representation of what the actual trajectory is like. So in that case, a uniform delta t breaks down, but we'll come to that. So that is something you'll have to keep in mind. We will stick with the uniform time grid. Okay. The next question is, fine, we sorted one thing. What about derivatives? How can we possibly quantify this idea of derivatives, right? So, okay, let's begin with a very simple. You might find it really simple that this is how we are going to approach this, but can you now tell me, like, what is the first principle definition of what a derivative is? The limit form. It has like a mathematical expression, right?
So as far as I remember, it will be limit h tends to 0. In the numerator, it will be f of x plus h minus f of x by h. If someone can verify, then it will be pretty nice.
Yep. Okay.
Yeah.
Okay. Yes, this is fine. So, okay. So what we'll do here is our f here will just be, like, say, theta. So theta prime, which is the derivative of theta, will be limit delta t tends to 0. Theta of t plus delta t minus theta at time t divided by delta t. Right. So we'll say, okay, let me just chuck the limit off and rearrange this equation. I get theta of t plus delta t equals theta of at time t plus delta t times the derivative. And just like that, I have phased my differential equation into some kind of a iterative dynamical law, which is at each instant of time, I basically told you how to take the previous angle, the angle at the previous time step, and how to get the angle at the next time step. This is kind of fishy though. I just threw away the limit. It does suggest something though, right? That is, this is obviously an approximation. It's not an exact result. What this does suggest is this approximation is more and more valid as delta t actually, we choose it to be closer and closer to 0. There is a different way to quantify this though. Here I have not talked specifically how the error varies with delta t, because that is an important thing in anything, not just computational physics. Any result you're reporting in your labs or something, you need an error gauge, right? You need some measure of what the errors are, or else your readings are basically useless. The same thing holds here also. So does anyone have some idea how could we possibly quantify in any way what the error of this specific thing we've done here is? Like writing delta t of this thing is equal to this. How good or how bad it is? Is there a way of quantifying that? Because the procedure we've just done is really, if a mathematician was here, he would kick me. So, anyone has any idea? If there's a more elegant way, maybe, to arrive at this result. Okay, no problem.
Taylor expansion of the function.
Nice. Taylor expansion. So, as usual, some things carry over from physics. We will assume that the functions we are working with are analytic, I think. So they are Taylor expandable in the neighborhood we want. So essentially what Taylor expansion in this context means is delta t plus t can be represented as, not theta of t plus delta t, right? Okay. Represented as this plus delta t times, right, plus delta t square theta double prime by 2 factorial, so on. There are infinite terms. So what we've essentially done is truncated the expansion at this point and then rearrange the terms, right? So this is basically what we have. This first line is essentially what we've used here. So in that sense, say that for a fixed time, some time, 5 seconds or something, these terms are going to be constant, the derivative terms. And if you change the delta t, you see how the errors are going to accumulate. So in this case, the errors accumulate quadratically. So if your delta t is like really large, your errors are also going to grow quadratically with delta t. So okay, this is good enough for us. We have at least some gauge. We know very loosely that if my delta t is smaller.
This is usually written as the order of delta t square as the error.
Yes. So the notation is called Unicode notation, which is written something like this. So this is like a common thing which is used in like algorithm complexity and all, computer science in general, I think. So yeah, this is what we write. What this means, I guess you can look it up later, but right, okay. So we have solved one more problem. We have written a differential equation in terms of some kind of an iterative solution. By iterative, I mean like you take the previous value, find the new value. Now you use the new value as the previous value to find the next time step, so on. So now let's rewrite our loss, our dynamical loss, which is namely theta of t plus delta t. We have is theta of t plus delta t times the derivative, which is omega of t, the second variable. And we also have one for omega, which is omega of t plus delta t times the angular acceleration, which is minus v over L times sine theta. So we will come up with a quick notation here. We'll say like tk is equal to t initial plus like k minus 1 times delta t. So it's like a arithmetic progression. So in that case, we'll write theta of tk, theta evaluated at tk as theta k, omega k, so on and so forth. So we have good notation now. And this also translates directly into a code also. these are like array indices or list indices. Fine. So we are basically done. So we have found out how to translate it because I now have a set number of points in time, and I know how to evolve my angle and angular velocity given an initial angle and initial angular velocity. That's it. I've completely specified my problem, and I can describe the pendulum with it. So now all we need to do is actually go and implement it. Okay. So how I thought these sessions could go is, I don't know, at least this part is like a basic model, right? So I was going to like walk you guys through it, and if you guys have like suggestions or like if I'm doing something really bad or if there are better ways to do it, you guys can suggest and code along with me maybe. We'll see how that goes as we encounter more complicated problems. But today's session can also like serve as an introduction to Julia as well, because this is like a really simple code to write. Okay, so with that, let us move on to Julia. I hope whoever was planning on following with me also installed Julia. So okay, so if you guys install these two packages which I told, which is Pluto, so UI and plots, these three are what we'll be using. So once you've done that, just run these two commands using Pluto and Pluto.run. Okay, I will maybe put that in the chat. Okay. So once you do that and run it, it should open a browser window just like Jupyter. Except as we shall see soon, it is superior in every way. Okay, is it opening? You guys are following, right? I mean, it's not too boring or anything.
Yeah, but
Cool. Okay, I will open this. This one was my previous attempt. In case we get stuck, it is good to have that as a backup. Okay.
Could you repeat how to install Pluto and the three packages?
Sure. So open Julia. It should open a command line kind of thing like this. And then you see the close square bracket key. Press that. Do you get which one I'm saying? Wait, I'll put that in the chat also. Sorry, this one. This key, the close square bracket. So if you just type that into the thing, it should switch. Your prompt should switch to this PKG in local. So once you get that, just do Pluto UI and plots. Yeah, got it. I don't know who asked me, so you'll have.
Yeah, it works. Right. Someone asked in chat, so you can go.
Okay. So yeah, so that's how you install it, and then you launch. So it should launch this window in your browser. And okay, click the new notebook. It takes a while. It takes a little bit of time at startup, so you'll have to wait a bit. If anyone has any other questions or something to add, feel free to do that now.
How long will it take to install? Because it's stuck on the very last plots things. Installing that
It plots is not. It's not in project manifest or registry.
Right. If you guys are on Windows, it might take. Are you guys installing which version of Julia? Is it 1.7?
Yeah, 1.7.
Okay, 1.7 shouldn't have that problem. Okay, if it takes like really long, like I don't know, maybe 20 minutes or something, just press Control C. It should pop out of that. It should just terminate it and then run it again. It might work then. Okay, I think. Oh no, why is mine also taking this long? Usually doesn't. I think this is why people usually don't do live coding sessions. There are so many things that can go wrong and debug on the call. Okay, let's see. We still have an hour. We'll see. Maybe I also restart.
In the previous iterations of Paratha, we usually had a notebook pre-prepared and this went through it. So this is like the first time we're trying a live coding session.
But I don't know. It felt we should do something more interactive or something like that.
Yeah, we can. If this can work out, it has a lot of things that can go. We can try it out.
Right. I have not prepared anything today. I mean, I have, but I don't know to walk you through my code. That will be like really boring. Rather, maybe you guys can suggest something. We can code it like that. I was thinking, but let's see. Okay, it launched quicker. Okay, so maybe I can tell you some things about if you're coming from Python and you've not tried Julia before. There are some what you could say like cultural shocks maybe, because the thing is Pluto is not an interpreted language; it's a compiled language, which is more closer to like C++ Fortran. So what it does is something called JIT compilation, which stands for just-in-time compilation. So the first time you run any piece of code in Julia, it takes a longer time because actually it is compiling the code from source, and then subsequent runs will become really fast as in the range of like NumPy and all in Python, or even in some cases the level of Fortran, which is basically like the gold standard for numerical
computation. If you could tell
computation.
the difference between a compiled language like C and an interpreted language like Python.
I'm not
sure if everyone is clear with.
I'm not sure if I am clear with it.
Okay, the basic difference in a sense. Why one is faster, why one is not.
Oh no, Dhruva is not.
Are there any online compiler we can use for the meantime?
Meantime of what? Wait, okay, my Pluto is actually loaded, so I'm ready. What about you guys? Is it still installing?
It's still installing.
No, my Pluto is ready.
Okay, that's good. Fine, then it's okay. This is the first session, right? We kind of pick up as expected. I'll continue, but maybe next time it's better if we are prepared, like installing stuff beforehand. Right. Compiled language, interpreted language, I'll have to get back to you, but very loosely in C++ and all, you won't find like REPLs in C++ and Fortran because it doesn't have a concept of taking a thing and taking one statement and evaluating it. Instead, it takes your entire script, all of the things, and then compiles it and then like translates it into like machine code and creates something called an executable file. And finally, you run that executable to actually get the results from your script. Whereas in Python and all, you just give a command, you get back a command. It does it line by line or something like that. I think that's the difference.
Yeah.
But
and that's what makes
honestly, I'm not. Right, that's what makes it so. Python somewhat gets around this by NumPy, which is essentially a wrapper around C++ code. That's why NumPy is fast because it's not Python. So, whereas in Pluto, like natively that kind of speed is there. The only thing is the first time you execute any code, it's going to take some time. So it will take long. It will take longer because it's not actually running the code, whereas it is actually compiling the code and then running the code. Once you compile it once, you're good. It will run really fast. So that's why we chosen Pluto. So let's see Pluto. Some things are different in Pluto than Jupyter. Maybe we should go over that also. So for instance, x equals 1. So some variable I was assigned as an integer 1. Shift enter to execute. Okay, just the first thing is taking time. Not even done it. Okay, fine. Very good. Okay, so shift enter to execute and then it gives some result. You can't write multiple lines in the same cell. Okay, so it's going to shout at you. So instead, we'll have to do something called a begin and end block here. It's nothing. Just simply what we'll be using begin and here is to encapsulate multiple lines of code in the same cell. That's all we'll do it. So you may ask why is it? I mean, this is like an extra complication, right? The thing is, Pluto is like really smart. The thing is, cells here do not matter upon the order of execution. If you use Jupyter, it depends on which cell you executed before this to see what the next cell is going to evaluate to. Whereas here it kind of builds a dependency. So maybe let me see. Let me try to show. Right, z equals 1 here, and then y equals z here. The 10 is back, okay. Then it just gives the last one anyway. So the value 1 you found here is actually the result of this. This is called an expression, okay? So an expression where I'm assigning the value of z to y. So any expression in Julia is going to evaluate to some value, either 1 or some float or just simply none. None means like there is no return type or something like that. So, but every expression evaluated is going to return something, and Pluto is just taking that return value and putting it here. It gives 1 here because z is 1. I'm assigning 1, so the result of this expression is 1. So if I change z equals 2 here and execute it, look what happened. It by default updated y and then printed 2 also here. So basically I didn't have to run this cell at all. Somehow Pluto has internally constructed some kind of a dependency such that it knows I'm creating z here and I'm referencing z here. So if I'm changing the value of z, it goes to show that this must be updated as well, and it does it for you. So that's a really nice feature for me, but if you're coming from Jupyter, it's going to be really jarring to work with. But it's really good, so stick with it, is what I'd say. Like just get used to it. So for instance, if I put y here, what is the value of y? I change it to 6, it assigns it here, and then it immediately changes it here. I don't have to run any other cells. As opposed to Jupyter, where the order of execution really matters. You see here, the order is like really weird, but it still works because that's just visual. I can also move these cells, throw it there. Okay, so see, once I've deleted, it's like z is not defined because it knows immediately something's wrong with my dependency. Fine. So let us begin. So if you guys have guys have installed the packages, what we'll do now is we'll say using package. PKG is the inbuilt package manager of Julia. It's like one of the best package managers in general, among languages. If you dealt with Python packages and dependencies, you'll know it's a big pain in some cases. It's not much of a pain in case of Pluto, though. In case of Julia. Right, so using package and package dot activate. What this does is basically tells the Pluto notebook to utilize the packages which you've installed globally, which you just did in the REPL I told you to do. So it tells Pluto, okay, take those packages. Otherwise, Pluto's default behavior is that it will, whatever package I use, it will install it by itself. So each Pluto notebook you create will have its own set of packages and versions. That's better in general, but for this case, it takes longer to set up. So, you'll have to wait more, and we've already been waiting for so long. So, once we've done this, we'll just say using Pluto UI. Pluto UI is, we'll see what it does and prompts. So this should take maybe 10 seconds. If you see, this is a difference from Python, because Python would instantaneously, if you put matplotlib or something, it immediately comes. This takes like 7 seconds because it's compiling all of plots from scratch for us to start with. Okay, so we are done with this. We are ready to begin with 55 minutes to go. Fine. That's bad planning on my part. Okay, one last thing I forgot. Okay, we were characterizing the pendulum, right? Like what is a pendulum? And we arrived at few values. We said the angular value, the angle from the horizontal, the angular velocity, the length of the pendulum. Anything else? Is that all? Is that all which characterizes a pendulum?
You need to define G also.
Okay, sure. That is like a problem.
The mass of the box.
Yes, the mass. And for display purposes, the radius of this box also. And is that it? Is that it? I think that is it. The only difference is these two first ones are dynamical variables. That means they're functions of time. These three are just like passive properties. They're not going to change over time. So yeah, you will just keep that in mind. That all. Yeah, the last one. The last one is the position of the anchor also. Need to know where it's anchored from. So that will also come within the properties. So anchor, which will be a coordinate pair x, y. Fine. So let's begin. To begin with, maybe you guys have heard of like classes or structures in other languages. Have you guys heard of it?
No.
Okay.
Like object-oriented programming classes.
Yes, that's what I'm referring.
I used that in Python once for a project, but I do not remember.
Okay, sure, cool, no problem. So Julia doesn't natively have like object-oriented programming, as it usually works in other languages. But okay, let's start with something more simple. Maybe there are some functions in general in Julia which are useful. One of which is type of. So if I say x equals 1, and then I ask Julia, what is the type of x? So x is a variable and it's carrying some value. It's going to tell me an int 64. This means it's an integer which is stored with 64 bits. So that's pretty large. If you calculate 64 bits, that's a large number of integers which it can represent. So if I change this to 1.0, it's now a float 64. Float as in floating point number, which is a decimal. Okay, so that's one. There's also another function which is nice, which is called dump. What dump tells you is the internal structure of a variable. Maybe say if I press dump, okay, where has it dumped it? In the terminal, it's dumped it here. So it says float 64 and 1.0. That means the first is the data type, and the second it's telling you what value it's holding, which is 1.0. So dump is going to be really useful because you can see inside what any object carries. So for instance, what about lists, right? The next thing we'd upgrade up to is lists. This is how you create a list. This is one way of creating list in Julia. It's basically just comma separated values within closing brackets. So what does it do now? Okay. So this it's a float 64 array of 3 values, 1, 2, and 3. Leave dump. Let us see the type of x. Why is it taking this long? Might be because I'm sharing my screen. In general, my resources are bad or something. I'm not sure. What is it even running? Yeah, that's nice. My notebook is found. Okay, anyways, so right, so we have a list. There is one distinction. If you see, it starts with 1, as opposed to Python and like many other languages. Indexing doesn't start from 0, rather it starts from 1. So why is this still running? I guess this gives time for whoever didn't manage to install Julia to catch up. Or we're both just waiting. Not good. Okay, maybe if there are any questions.
And the kernel in this, or does that not exist in Pluto? Like restart the kernel, how we do in Jupyter?
Well, no, I just have to come out of it entirely. It just gave the result. Now I think it's done. Now it gives it. Okay, fine. I think we're good. Oh, it got stuck on some process, I think. Because when I press Control C, it just popped out of it. Okay, we're good. And so, what I wanted to show was, why is it not deleting? Something's weird. I will have to check that out. Okay, so when we see type of x now, which is a array, it says it's a vector and some weird curly brackets and then float 64. What this means is it's a vector of float 64. which is an alias for, in general, what is called an array. An array doesn't have to be one-dimensional. That's the only difference. So array can have this one here represents the dimension. So I could have like put a list in list, for instance, like.
If I may add something, like arrays, vectors, matrices, they're literally all the same thing. You've been taught they're different in your +2, but they're all the same thing essentially. So like I think Akshay will use me. I would use them, even Akshay would use them interchangeably while coding. So
Right. Arrays, vectors. Vectors are generally, like one-dimensional arrays. Matrices are also arrays. Yes, he's right. So it's also an unnecessary distinction, right? In a sense, they're all just a list of numbers.
yeah.
It carries more relevance in physics. You call things vectors there. It means it transforms in a specific way. So that's not the lingo which we are using here, but yeah. Okay. So it works here. Okay. Maybe we should not do this. Never mind. Leave this example. Fine. But anyways, that's how you make a list. Okay. That's how you make a one-dimensional array. So there are no NumPy arrays and all. So this list here. Okay, I'm going to stop using list. Okay, in Julia terms, it's called an array. So this array here is like the equivalent of a NumPy array in Python. There is no list equivalent per se. You can also have other data types. I can have a string also, and maybe a integer. So now, if you see, the data type changes to any. What this is probably the closest to a general Python list. So because you can throw anything in there, and it's going to consider it as a array. So, but usually you don't have a use for this much. So as you can see, there are a plethora of like data types, right? There's the vector and there are integers, floats. There's also int32 and all, like different bits of storage. There are so many more. So the thing is, Julia and many other programming languages allow us to also define, in some sense, our own data type, which in essence means like we can use the existing data types to create some kind of a composite. So what I'm going to do here is, it's called a structure in this case. In general, like classes are somewhat similar, but it's not meant to replace a data type per se, but you can think of it like that, like you're writing your own data type. How does a pendulum behave? I'll create a pendulum data type. So I can create objects and say that this object is a pendulum. Similar to saying like 1 is an integer, 2 is also an integer, but 1 and 2 are like distinct objects, right? Only similar in the way that both of them are integers. So they share some common properties, maybe like, how they behave under division, how they behave under addition, so on. So the keyword here is struct. I will say struct pendulum. Okay? I'm creating a structure. I need an end. Okay, also that's one more difference from Python, I guess. So any statement in any block, as we would call it, in Julia has to end with the end. I mean, the last word should be an end. So this signifies one block, as the thing is showing. Whereas in Python, it's like maybe class from pendulum. You'll have to put a colon here, and then that's it. You'll have to indent your statements instead. You don't have an end and all. So that it works by indentations. Here you don't have any colon or anything. It's just you start a statement and you end it. So that's how it knows where you started and ended. Okay. So now I'm going to give this structure some parameters. We just discussed what makes a pendulum, right? So I will say for start. This is one more cool thing in Julia. It can work with Unicode characters. Essentially, you don't have to write theta anymore. It can be like really cool, right? This is like the LaTeX command for theta, right? You put a backslash. Backslash? No, it's just. This is the backslash.
I think it's backslash.
Right. So you put the backslash and you write theta. And now you press tab. It turns to the Unicode character for theta. So it looks nicer. It looks more closer to math. So I will say my first parameter is going to be something I call theta. And I put 2 colons to specify what type it is. Is it an integer? Is it a vector? Like, is it like a coordinate or something? Theta is just going to be a float, right? It's just going to be some decimal value. And we know that comments are labeled by hash also. So we know that this is in radians. And radians are like the natural units to work with. Degrees are more like suited for us, right? So we have the angular position, and then we have slash omega, and then press tab. Tab completes it, okay? So you get omega, which is also a float, and this is in what, radians per second, I guess. But this is basically the angular velocity. So we have our two dynamical variables set, and now I have length, right? I also put length of the pendulum, which is also a float 64, and the mass is also a float, and the radius, which is also a float. So these are my things. And there's one last thing, which is the anchor point. What is the anchor going to be? So anchor, essentially, I'm looking for something like anchor. I'm looking something for like two-dimensional vector. So like something like 1, 1, something like this. So this is what I'm expecting. And does anyone remember what data type this was? It's okay. You don't have to remember. We can just quickly find out. Type out. So this is a vector of float 64. So take that and put it.
So I have a question.
Yes.
Do you need to write the data type of the variables? Is that a requirement, or are we doing it like, because in Python you don't need to write the data type?
I think it is a requirement. Okay, in general, if you do it like that, if I, like I'm writing x equals 5 or something, it works, right? Okay, it doesn't like x equals 5. It works, right? I don't have to tell it that's an integer, it knows. In general, it does work like that. You don't have to declare the data type, but I think I think inside structures you have to. Let's see if it works without this. Okay, I guess it's fine then. But in general, it is a good practice to actually label the types, not just for like looks and all. It actually has like some utility, because there is something in Julia called multiple dispatch. We'll not cover that right now, but it's like a really powerful feature of Julia. So for utilizing that, you need to specify the type, because once you let the compiler guess what type your data variables are, it has to come up with many possibilities of functions. It's like, I don't know what you're going to give me. So based on what you give, I will construct that function. So it's like, oh, you're going to give me a float value. I don't know beforehand, because you never told me you're going to give me a float. So it's going to be waiting for you to give something, and then, okay, I got a float. I will construct the function such that it takes a float and performs the operations. So in doing that, it becomes slower. So instead, if you tell it beforehand, so it will pre-optimize it for you. We'll go into that later when we come to multiple dispatch. But basically, our structure is done. So this is like an equivalent to saying what is an integer or what is a float, in a loose sense, not very tightly, but some kind of an analogy as a pendulum data type. So I will create an object variable, which is a pendulum data type. So it is a pendulum. For our intents and purposes, it is a pendulum, because we've abstracted all the features to be these variables or these properties. Okay, so the first angle, the first thing is the theta. So when I create a pendulum, if I do it like this, it's going to shout at me, because I have not told it. See, it says no method matching. This is this dot pendulum, because I've not given it any of these values, so it doesn't know what to create. So this is how you create objects. Sorry. So it's like a function with the same name as the struct. I think generally this holds in any programming language or classes and structures. So you start a pendulum, and then you give the values. So what angle? Let's give, I don't know. It has to be in radians. So pi 180 over pi, or pi over 180 times 45. So 45 degrees. And angular velocity, I'll give it 0. Length maybe 1 meter. Mass kg. Radius 0.2. Maybe. The anchor will be maybe 0.1, and the length is 0.0, right? So this is like saying the anchor is at 0,1, such that the bob will exactly hit the object. Right. Okay. So if I do this, I just create an object. Now it's fine. Now it's happy with what I've given it. And thanks to Pluto's nice interface, I can open it and see what the variables it has assigned. So, right, this is what we wanted. We have now created what is a pendulum object. Cool. So is it clear this much? Because these are new concepts, it might be a bit confusing. So what we've essentially done is created our own pendulum type, in a manner of speaking.
Why are you writing the 0 point, 1 point in that format?
This is basically the order of writing these.
Why are you keeping point after every digit?
If I don't give a point, it will think I'm giving an integer and then it will shout at me, I think. Does it? Does it shout at me?
Yes, it does.
Oh, here it does. I think usually it does. It's not shouting at me now. I think it's smart somehow. Right. Julia's also sometimes it catch some information. Okay, maybe that's not relevant here, but fine. Yeah. Generally, it does shout. Maybe in this case, I don't know. I've tapped into some part where it doesn't. But when you specify float, probably it's a good idea to put points. So, if you're dealing with a float, I'm pretty sure it's functions it will show. I guess it's a good point to also introduce how to write functions. There are two ways to write functions in Julia. Let's write a simple one to like square a number maybe. In Python, you would go something like define function name, like square, give the variable, do this, and then what to return square, right? Oh no, in Python it's this double asterisk. In Julia, it is kind of similar, but the keyword instead of define its function square, and you give the variable and no colon and the function, and inside you return x square. So here square is just the caret symbol as we're used to it. Okay, so it has defined one with one method. We'll come to what a method means sometime later, maybe in a future session. But so now if we try the square, you note that I've not told it the data type here. So if I give anything, it's going to work. Actually, that's not strictly true. Anything for which this x square is like a valid operation. If I give a string, will it work? I think it's going to shout at me. String. Oh, it works. So can someone explain how this works? This is actually a very interesting feature of Julia. I gave a string and somehow it squared the string. They make it purport. Does it still work? Nice.
Hey, is it like concatenating the string or something?
Yeah, the thing is, here you see this caret here. I have this caret is actually a function. Okay, all of the binary operators. If I write it like this, as if that is the function name, and give like I don't know 2, 3. So this is like 2 to the power of 3. It actually gives me 8. So this is actually a function, and this notation, right, x caret 4. That is like a syntactic sugar basically, just some convenience that the people have coded in for us. But in essence, it's also normal functions, just taking two values, and so I can call it like if I do plus now, it's going to give me 5. So the thing is, this is where multiple dispatch comes into play. If I define this product operator on any two objects, these two are integers. So someone has defined it for it. If you use this function, multiply them in some way. So, and I guess this caret operator, the exponent operator, just calls upon repeated multiplication, it looks like. So since this function is defined, it manages this. So since for strings, apparently then the multiplication operation has been defined as concatenation, I guess. So since this is like, again, I don't know for sure, maybe we have to look into the documentation, but it's implemented as repeated multiplication, at least for integers it seems. So then it knows exactly, okay, I have multiplication, this is repeated multiplication, okay, I'll just concatenate multiple and return. So that's where data types come in. So you can create this multiplication function to work differently for different data types. We could make a multiplication function for a pendulum type also to work in some different way, such that if I do pendulum 1 multiplied by pendulum 2, it will give you some result. Whether that's meaningful or not is up to you. But right, so I guess if you change this to 2.0, now it might shout. Now it shouts. Because it's a float right now, it's not implemented as a repeated multiplication. So you see what I'm getting at? This same operation, like differently for input values. Having the different types of input values. So when it's an integer, it's good with it. Okay.
It's just like the same as function overloading kind of thing which I have in C++.
Very similar. It's very similar actually. And in some ways it is very not similar also. But we'll discuss those sometime else. But for a working definition, you can think it's somewhat like that. Like
Okay.
the same function for the thing. The thing is in function overloading, right? Okay, I think at the level we've discussed, they're pretty much the same. So we'll go with that for now.
All right.
Fine. Last thing is one more thing. You don't have to write a return statement actually in Julia. Whatever is the last statement, last expression which is evaluated before this end, which is here x square, it just returns that. See, this function still works. If I write like 4 or something, it still works. Because by default, you don't have to write return. It just returns whatever it last evaluated. So if I wrote x square here, also this might seem weird, right? I've not done an assignment. I've just thrown an expression in there. But it still works because it doesn't have to. It just evaluates line by line each expression, and whatever is the last one, it just throws it back at you. So if it's x times 2, it's going to give you 8. This one is like lost basically. So you don't have to write return, but generally I write return anyways. More apparent what the intention is. Fine, we have gone through functions. I guess we also should quickly go through loops, right? For loops maybe. That is an interesting object in Julia. In Python, you write something like for I in range 5 or something like that, right? So the equivalent here would be, firstly, indices start from 1, okay? That is going to be a big bottleneck if you're very used to 0, but it's not that significant beyond the first discomfort you have with it. So you say 1 colon and 5. So, and I'll say print type and end. Again, this is a statement, this is like a block, so I have to add end. So if I do print type, right? So once I've executed, there's no square function anymore. No? So this is now shouting at me. I had a dependency there and you just deleted it, so that's fine. I'll just delete this one. In Pluto, if you try print statements, it doesn't print it actually here itself. Instead, it prints it to the REPL. So that is one thing. Did it even print? Okay, didn't print that. Wait, let me. Yeah, I'm not sure. Okay, maybe we should not use print at all. What if I just put I? Or maybe I just do this demonstration of the REPL. That might work. I do for I in 1 is to 5. Then tab, print I, end it. It's printed 1, 2, 3, 4, 5. So let me put print line. Right. So this works pretty much same as in Python, I guess. Just the thing is the object now is 1 is to 5. Not is to, but 1 colon 5. What is that object? Maybe let's look into that 1 colon 5. What is that weird object? Just gives it back. That's not helpful. Maybe type of. Okay, it says unit range of integer. So what does that mean? So it is some kind of a range. So unit range is suggestive of the fact that where is it? It incremented by 1, right? I didn't specify the increment. I have specified the start and stop, and it has by default taken the increment to be 1. So that's why it's called a unit range. Let's try dump. Maybe dump will give us this outputting to the thing. It's not. Okay, I'll just put it here. Dump of 1 to 5. Okay, so it says it's of type unit range, and it has 2 parameters. It has a start and it has a stop. The start is an integer with 1, the stop is integer with 5. So it's not actually carrying an entire list. So that's the thing. This is like a special object that it doesn't evaluate all the points in that range until you actually ask for it. I think the range in Python might be similar. I'm not sure. If you want to collect this into a list, like I want all of the elements in this range, you just write the function collect. So collect of 1 to 5 give you a vector with 5 elements, which is the what constituents of this 1 is to 5 object, the unit range. I can have non-unit ranges also. I can have 1 to 5, 1 to 10. I think this should step from 1 in steps of 2 and stop at 10. Right. So Yeah. So basically, yeah, this is all we'll require. But you don't need to use the collect when you're in a for loop. When you're in a for loop, it knows that this object is something I can loop over. So I can like ask what's the next one. And then it says, okay, 1 plus 1 is 2. Oh, you're asking me again, okay, it's 3 this time. So it doesn't have to be a list where I know all of them like beforehand. In fact, in the for loop, what I'm looping over doesn't have to be a range either. It doesn't have to be a list either. It can be many other things. But okay, that's also general programming thing, not this Julia specific. But we'll see that. We'll see that when the opportunity presents itself. Maybe now it's more weird that I'm just randomly saying stuff. Okay, let's get back to the object which we created. We created a pendulum, right? So it has a problem whenever I dump it, I think. It gets stuck. Right, it cancelled. Right, when you get stuck, just go to the REPL and put Control C, okay? It'll interrupt whatever it's doing and just stop it. Right. Okay, so you created an object, right? So how do I ask? Now I have this object. What is this object's angle at the moment? I'll say, okay, object, the syntax of this is dot. Dot means I'm asking the property of my object. So here I put theta and then tab it, and I get what the theta actually is. So if I put omega, tab it, I get 0. So this is how I access the properties. This syntax carries over in all other languages. You usually reference using dot only. Okay, so now we have created a pendulum. We know how to access the properties of our pendulum. What's next? We want to evolve it, right? We want to watch it swing. Is everyone following till now? Am I going like really fast or like erratic? Because we just jumped through a lot of things. I've also not been looking at the chat. Okay, that's fine. I'll continue then. Okay, so now what we have to do is try to evolve it. Okay, let's begin by calculating the force at a given instant. What is the force acting? Well, force, by force I mean in this context the tangential force. It only changes the angle, right? Since the radial part is covered by the constraint of the rigid rod. So I will write a function, define a function. Function get force or something, maybe get force. And I will pass it an object which is of type pendulum. That means I want to get the force on the pendulum at this moment. Okay, so that's the intention of what this function is intended to do. So what will this compute? Get force. Get force is actually, do I have my other screen again? Okay, let's see. Terminal partial. So here we can consider this part to be some kind of a tangential force divided by the mass, right? So what we are trying to write here is a very general code, so that we can take this code and apply it to something that is not a pendulum also, making minor tweaks and it still works. So in some ways, our setup is still pretty contrived to a specific pendulum, but the general context I'm trying to set up, because I don't need to get this force. I already have, I know that these are the two equations I'm doing, but for some reason I'm separating out this as a different function. That will become more apparent when we try to expand our horizons beyond just a pendulum. So we will start with computing the force. The force requires what? Gravitational acceleration, the current angle, and the length of the pendulum. So all I'm going to do now is return minus gravitation. I didn't have the gravitational constant, so maybe I will put this as a parameter here. So when I put a colon, when I put a semicolon here, this means that these whatever arguments I'm specifying after that are something called keyword arguments. That means, okay, maybe I'll not go into keyword arguments. I'll just use a comma and create one more. C, which is a 9.8. I'm giving it a default value. I think you guys will be familiar with default values, right? So I'll just quickly go through that. Some function which takes two parameters, x and y. I give y a default value of 2, and then I return just x plus y. So now if I call this function 2 and 3, it's going to give me 5. But I also have the option of calling just function of 2. Now it gives me 4 because it takes y equals 2 as a default value, as the name indicates. And if you look closely here, it's not saying generate function of one method, but rather two methods. Because when I write this function, it knows that I will either call it with the value of y, or I'll just not give you the y at all. So in that case, it takes 2 and puts it in here by itself. That's why it's created two methods for it. It means there are two different ways to call this same function. Just one argument or with another argument. So I'm giving g as default because I don't want to keep mentioning that it's 9.8. Maybe the negative should be on this. That makes more sense. So g divided by L. The L is the property of the object, right? So I have an object which is a pendulum, and how do I reference this value? I just told you the syntax would be dot L. So it takes whatever the length of this is and gives me. Then I multiply it with sine of the angle, object dot. So just like that, I have got the force at a specific instant of time, right? If the angle is this, the force is going to be this. Okay.
Hello.
So, yes.
That obj double colon pendulum means, are you defining obj as an variable, or is it some default name for an object?
Object is just a variable. I can name it as anything. I'm just saying some variable which I'm calling obj, and it has to be specifically. It has to be a type of pendulum. If I try to call this function with any other type, it will start shouting at me again because it doesn't know what to do. Yeah, did that clarify your question?
Yeah.
Akshay, your
Okay, so this
course
is it wrong? What? Oh, that also means a mask, right? Object.mask. Thanks. Are you saying something? Are you still here?
Yeah, I'm here. My internet went for a second. Sorry.
Okay.
So your equation for the first seems wrong. Why is there a by L? It's dimensionally wrong.
Well, okay, maybe it's wrong to call it a force then. It's more of a torque, right?
Yeah, it is the torque. Then it should be into L.
But I just want to take this and put it into my equation. Maybe this setup is wrong, then I shouldn't be calling it a force at all.
That's alpha, right? That's angular acceleration, right? So you can just call
right.
it
Hence, this would technically be the torque. Okay, maybe I'll just rename the torque. Okay. Right. Okay. We'll work with this. Work with this for now because now it's fine, right? If I call it a torque, does it still not work?
Yeah, we should times r square, right? To get torque. We have to multiply I with alpha.
Does not work. Maybe we'll just eliminate this function then.
You can just write to get omega, no? Instead, you can write it as get omega. Or like get.
We could, but that's going in a different direction. We don't. I don't know why that would be useful. Okay, let's just write the most general way and then see if we can start breaking it out into more functions. Then we'll just write something called wall.
One second. Someone told us alpha, right? I think it is alpha. It is angular acceleration.
Yeah, it is angular acceleration.
It's alpha, right? So it will be like torque over I.
Yeah, just remove the m and it will become.
Yeah. Okay. So you want to call it get alpha, then that works too. That's Correct. Get alpha. Sure. Okay. So this works. This works. Fine. Okay. Now that we've gotten alpha.
OBJ, sir. OBJ colon.
Oh, that one. Cool. We good now? Yeah, I think we are good. Right. Okay. So now we know I've gotten my alpha. Next, I can say update the position of my object, which is a pendulum. So basically, I'm going to write this block here into code. So I write. I also need one more parameter. Here I need something just delta t, the time step, right? Because I need a time step. So in this update function, I will require a time step, which is a float. Okay, so now what do? I will take the objects theta, then I'll add to it. First, I'll update the omega, right? I will take into account the force. Okay, so this is just object of omega. Take the older value, then add to it the alpha. Okay, the delta t. Delta t times get alpha of the object.
I think it should be object dot omega, not w.
Oops, thank you. So this one translates exactly from this, right? The only thing is this t plus delta t and t is not apparent here, but what this does is takes whatever previous value it had and utilizes it to find the new value and then assigns it to that same variable. That's what this statement means. So we could have taken this line now, and just put it here directly. It would give the same result. Like instead of wrapping it in a function, would have just done this. But it's more extensible this way. That's why I called it force. Well, now it's not a force though, but okay, we'll see. We get to the end of this, it'll come apparent why this might be useful. But sure, okay. This is one way to write it. The way I prefer though is like we are taking the old value and then updating it, right? That is a shorthand operator for this. It's just like plus equal to. What this means is take the old value, add this new quantity to it, and then assign it to the same variable again. So what we wrote before is equivalent to using plus equal to. So now I write object dot theta. That's plus equal to delta t times object dot omega. Right? Okay, it has updated the positions. Is that over? That all we wanted to do an update? Yes, I guess so. That's all. The thing is now this won't work actually because let's try now. Let's try, and it's going to shout at me. Let's see why. I have an object. This is a pendulum which I've defined here, and a delta t 0.01 maybe 0.01. Okay. So it says immutable struct of type pendulum cannot be changed. So by default, when you create a structure in Julia, you can't change the parameters, or you can't change the data which is inside it. So I'm not sure why. I think Dhruva can explain why that's better in some cases. But in case we want to make it changeable, I'm going to take the simple way out here, right? Mutable struct, and it will suddenly become mutable. Now it's fine with it. In some cases, it's not good. I think it hits the performance. But we're not bothering about that right now. As of now, I've told it's mutable. That means I can mutate these values, meaning I can change the values. And I have changed it here without any issues. Right? So now if I say object.theta, it actually gives me a different value. It got updated here also, right? That's nice. So every time I run the cell, it's actually changing here. So does it also change that if I write object? That one's not changing. Oh, it doesn't recognize it as a dependency, I think, because this doesn't qualify.
Yeah. That's why, I mean, in Pluto, if you want mutability, you have to be careful.
I see. Makes sense. Fine. But as you can see, it is actually updating. It's just Pluto's not recognizing it. That's fine. So I've updated the object.
Isn't it easier to use an immutable one? Because anyway, you'll end up plotting it, right? So instead of creating copies.
Copies of?
So
No, doesn't that it have to override the object, right? Every time I update, I'll assign a new object to it.
Yeah, so you are basically making it immutable only, no? So might as well just leave it immutable, and instead of calling update, you say you are basically getting a new pendulum at the new position. Store it into the same thing. It's the same from the point of view of code. It's the same thing.
Right. I have not rehearsed with this, so I'm not going to proceed with that.
Sure.
Because it inevitably costs more to say. But yes, what he's saying is like there are multiple approaches to going about any problem, and in some cases they have their own merits. I think Dhruva's approach is more, I'm going in a more roundabout way. I'm doing the same thing by unnecessarily introducing complexity. But if you guys are trying it on your own, you can implement it.
One more thing, your update function should have an exclamation mark.
Oh yes, good point. In Julia, there's this notation, okay? There's a convention, okay? You don't have to follow it, but it's better if you do. So whenever I mutate an object, that means if I give an object and I'm actually changing that object somehow and not creating a new object, in that case, I put a little exclamation mark at the end of the function name. Or as in Julia, we call it a bang. So I call it update bang, okay? So what that means is it's indicating that if you use update bang, that whatever object you're giving in, it's going to be changed. So be aware of that. So this is a convention followed across most packages like this. So generally there'll always be like two sets of functions. There'll be an update and update bang in case people, depending on the use case, you would either want to mutate an existing object or you'll want to create a new object and then do whatever you want with that. So in this case, it is good to put a bang at the end. Here we're not doing it, if you see, because we are getting alpha, but we're not altering the object in any way. We're just doing computations using it. So no bang here. You'll come across it in plots, I guess. Because, sometimes you want to plot on the same canvas. Sometimes you want a new canvas entirely. So the bang will be useful there. Right. So we have done an update function, get alpha. What do we want next? I was actually going to create a trajectory variable here, but what Dhruva says invalid is that you could just plot it, one by one. But I had done it like this because once I calculated this theta, I have a way of evolving angle, but I don't know what the angle was at some specific instant. If I want to correct that later, I'll need to have some kind of a trajectory variable. It's like a list of variables. List of values. At each instant, whenever I update it, I just take that value and put it into trajectory. Okay, at instant 1 it was 0, instant 2 it was 0.01, something like that. So in the end, I can...
so your trajectory, instead of being trajectories of thetas, you will have a trajectory of pendulums.
Objects instead, exactly, right. So that would be the other approach, which is equivalent basically. I guess it's better in some ways maybe. Yeah, that's up to you guys for thinking.
I could not get the last statement, like trajectory of, instead of trajectory of thetas, it will be trajectory of objects. Like I could not get that.
It's fine. I think maybe Akshay, you continue, and
we'll discuss on Discord. I guess we can put our progress in different ideas and all later. Because right now we have 10 minutes and there's no way of completing anyways. I'll just try to finish the main part, I guess. So I was going to have a trajectory field in the same structure. Basically, it's going to store all of the angles. Okay, so at every time I call, so this is meant to be a vector of load 64. So that's later when I'm plotting, right? Okay, now this is shouting at me because I've not given it any trajectory, right? Because now I need to provide an initial trajectory. I just give it some list. That is also bad practice, but in the interest of that being only 10 minutes, I'll just stick with this for now. We'll revisit it later. But okay, now we're given it an empty list for the trajectory. Initially, there's nothing. Ideally, I should give the initial position in there, but that's fine. We'll deal with that. Or maybe I'll just put that in there. There are better ways to work with it, but okay. So initially, I'm saying the trajectory has a single point, and that is the initial position. And this is like the current values of the data. Okay, so now whenever I update it, right, I want to store that into the trajectory variable of the object. So the object has a history of its own trajectory. That's basically what I'm implementing now. The object, the trajectory. I want to append in the language of Python. In Julia, the appropriate function is called push. If I write 1, 2, 3, if this is one array, X, list of 3 values, I write push bang. Push bang because I am altering this vector, right? I'm adding a new value to it. So put a bang at the end. Push bang X, which is the array I want to push into, and then the value 4. I think this should work, right? So now it creates a new one. And if I see X, right, X is actually updated, right? I guess Pluto doesn't work again because of mutability, right? So X has been updated. So push bang is what we want, which is the equivalent of append. So I will say once you calculated your new things into the trajectory property of the object, push the theta. So every time I update, I will record what angle it is newly occupied. So my update function is over. I've gotten an alpha. That's pretty much it. Now all I have to do is evolve this. That is actually put this into a loop. So I'll put function evolve. I guess technically it should be an evolve bang again. It takes an object, which is a pendulum. It takes a delta t float. Does it take anything else? I feel like it takes something else. I'll also have to tell it how long to run it for, right? Sorry, yes? Someone was speaking. Is it Dhruva?
No, I just said that how many times, max number of t, max t,
right,
whatever.
Right. Exactly. So, like, number of iterations, perhaps. Which basically tells me how many times I want to step forward in time. So, that is the equivalent of specifying the stop point. Because t belongs to a domain now, right? Just initial time t naught and some final time tf, space by delta t. So basically, I'm telling it how many distinct values I'm taking in this domain. There's like number of iterations, how many times I want to step forward. So if I multiply delta t and number of iterations, I get the time, like actual time elapsed in seconds, I guess, of the overall simulation. Fine. So I've written function evolve. That is, I've created an update and get alpha. Now all I have to do is actually update it in a loop. So I will write for I, or like maybe time in range. The range, as we discussed, will be 1 to number of iterations. So this gives a value from 1 to number of iterations by stepping forward plus 1 every time. Again, put an end for this statement, and then what do you do here? You take the object and then you just update it. It's the object with delta t. Is that all we want? Right. And in the end, just return back the object. This is not technically, we don't need to return the object back. Maybe, okay, I'll just return it for, I don't need it because this is evolve bang now. It already alters the object. So in that case, generally we don't return anything. Maybe I don't return anything. Okay. So what is this is because I've update banged it. It has pushed the trajectory and all. So what this evolve function essentially does is it gives the object its history. So the object has its experiences inside it. So I don't need to create a new object or something. I don't need to return anything. That is, if I do, okay, let's try it now. Evolve banger, my original object which I defined up here. Time step 0.01 maybe. Number of iterations, 10. So what happens? No method. What's wrong? 10 point. So this is why I was putting the points earlier, because I've specified it's a float. It's not even a float actually. It's an int. Number of iterations is an integer size. In that case, it should be 10 only. And let me define the object again in use. Fine. I'll just remove this. So in the same cell, I have to wrap it with a begin end. So this is again because of Pluto's restrictions. If I want to write multiple statements, I have to wrap it in a begin end block. Right. So when I do this, let's look at the object. Has anything changed? It has evolved it in 10 time steps. Okay, some values are here. Oh, and look here. At the trajectory, it now has 11 points. That means it has evolved for 10 steps and then it has stored what all angles have accumulated in that time. So now basically I have the trajectory of the pendulum over these time steps, which is a grid from 0 to 0.01 steps till like 10 times. So it's 0.1. Right. So I mean the time steps would be like 1 from 0, 0.01 to 1.0 I guess. Great. It put 100 or 0.02. Oh, what am I even doing? How many steps did this take? Maybe I'll get right at it. Start equals 0. Stop, I don't know, stop. Step equals 0.01. Then equals 10 times, right? 11 times. Okay. So these are the. Why is 0.01? Okay, I don't know what I did, but at these time steps, basically I've evaluated the position, the angle of the pendulum. So this range, I'm just doing the same thing. I'm just specifying the start, step, and length. I could also, like not percent length and instead write stop. It's like, I don't know, like 1.0 or something, and it would do that also. So this is just the range function in Julia. Okay, so that's it. We have found for these time steps what the position will be. Cool. What we are left with is visualization, which is plotting and maybe like comparing with multiple pendulums. But I guess we don't have time for that. We are already at 5 o'clock. So perhaps we should continue that in another session.
Or for now, just
we have now set it.
Maybe you could
what?
plot it, I guess.
For now, just plot a scatter plot, like one dot that moves to the left.
Yeah.
Okay, I'll fuck dude. Like all of this nice work we've done for 2 hours.
Yeah.
Shit plot we'll get. Because the plotting is a bit involved. I think it would take like half an hour or so to explain, and we have an interesting talk at 5 also. So next session, but I don't want it to be like next Saturday. That will be too much of a break. Do you guys have any idea when we could have something closer? Because we'll have meetings also after that. It'd be good if we quickly cover the plot also sometime soon.
We can do it tonight or tomorrow.
Yeah, I'm fine with that. You guys can come up with the time. I'm fine with that.
Okay, I'll
so maybe
Discord.
Sure. So I guess that is where we stop.
2 days.
Hmm?
We'll try to do it in the by tomorrow. It's very connected.
Yeah, it is, and it'll look good because it'll finally pay off, right?
Yeah.
So I hope you guys understood. If you have any doubts, just message me on Discord. If you're not joined in the Paratha Discord group already, do join because we have a lot of conversations there and planning for other events. So yeah, that's about it for today. I guess thank you all for coming. It was nice to see like.
Will it be possible for you to share the notebook on Discord?
This one which I've written just now.
Yeah.
Sure.
Yeah, thank
but
you.
I would
you upload it on the web page, the GitHub page that you made?
Yeah, we'll do that.
I'll put it that page.
Yeah.
Cool. So yeah, that's it. Thank you all for coming. Bye.
Yeah, thanks for coming. Bye everyone.